Okay. All right. What is the electron? I still haven't got to talk to my friend about how to reverse these images on that. There's probably like I said, there's a real simple setting, but I don't know anything about computers, so I'll have to ask my friend how to. So, okay, this is one of my least popular videos series so far. Has been the book review of What is the Electron by Volodimir Simulik. But I'm just going to do it anyways, because whenever I read a book, if I read an interesting book, I like to share it. And it'll be up just in case somebody wants to watch it. This is the third part, this is part 3. Now you guys, anybody's keeping up with my channel, you better watch me on LBRY, because get used to that, because YouTube's about to take me down. They've been taking videos left and right. They just took one of my most viewed videos in recent times. It was called "Is David Icke being trapped by the New World Order?" Now you can watch it on LBRY. They took it down on YouTube. But basically, that video was about David Icke's solution about all coming together. And I'm just saying that's not realistic. People are really not meant to be together. The different kinds of people want to live in different kinds of societies. And so bringing everybody together is sort of like what the New World Order wants to do. And, my solution for the New World Order is to have we call it scumbag clearinghouse, where you put bounties on these people, and it's like a blockchain crowdfunded bounty hunter website to give people rewards for taking out the scumbags. But anyway, I'm going to start with this. Let's get back to this book. This is part 3. We got up to this is the author's paper. Basically, what this is a survey of different theories of the electron. And the electron, there's a big conundrum with exactly how to interpret what it is, because if it has extension in space, it should explode by its self-repulsion. But if it doesn't have extension in space, then what is it? There's no such thing. It's a point particle. That's not a realistic entity. So what happens is that if you treat it as a point particle, that you can get somewhere mathematically. And if you treat it with something with an extension in space, it's there's also ways to treat it mathematically, but it suffers from that problem. How do you really interpret the configuration, the actual ontological reality? Anyways, the electron is a system of classical electromagnetic and scalar fields by Volodimir Simulik, Institute of Electron Physics in Ukraine. The electron is described as a system of classical electromagnetics and scalar fields. A coupled system of two bosons, that's photons and massless boson with a spin 0. A mathematical proof of electron structure is given. The main properties of the electron are explained without reference to quantum mechanics or quantum field theory. The slightly generalized classical Maxwell equations are proved to be the equations for the electron. Introduction. 19th century conception that matter is electromagnetic nature is extended here to the idea of more complete bosonic nature of matter. This means that all bosonic fields, not only photonic and electromagnetic, are treated as sources of fermionic fields, which therefore are the consequence of bosonic fields. Okay. And put the music back in the background up a little bit for myself on my monitor. Okay, there we go. The first elementary particle, the electron, is dealt with here in order to demonstrate the possibilities of this idea. It must be stressed that the electron is not an elementary object, but has a structure. The electron is presented as a system of classical electromagnetic and scalar fields, a standing electromagnetic scalar wave in its stationary states. In other words, the electron is treated as a coupled system of two bosons, photon, a massless boson with spin 0. The proof of this assertion is presented below on the basis of the following four arguments. The Maxwell-like equation for the electron is unitary relationship with the Dirac theory, the symmetry principle, derivation of atomic spectra from the new equation. Our non-quantum mechanical model of the microworld is a model of the atom based on slightly generalized Maxwell equations, that is, in the framework of moderately extended classical microscopic electrodynamics of media. This model is free of probability interpretation and can explain many inner atomic phenomena by means of classical physics. Despite the fact that we construct a classical model, in building it we use essentially analogy with Dirac equation and results achieved on the basis of this equation. It should also be noted that electrodynamics is considered here in terms of field strength without any reference to vector potentials and the initial variables of the theory. The first step is to define the unitary relationship and broad analogy between Dirac's equation and the slightly generalized Maxwell equations. The symmetry principle is the second step. On the basis of this principle, we introduce the most symmetrical form of generalized Maxwell equation, which can now describe both bosons and fermions because they have both spin 1 and spin 1/2 symmetries. Moreover, the equations are unitary connected with the Dirac equation. In the third step, we refer to Schellhofer, who suggested the possibility of introducing interaction with the external field as interaction with specific media in Maxwell theory, a new way of introducing interaction into the field equation. Nevertheless, our atom and electron model is essentially different from Schellhofer. So we have used another unitary relationship with Dirac theory. On the basis of these three main ideas, we are able to construct an electromagnetic model of an atom and atomic electron. Interest in the problem of relationship between Dirac and Maxwell's equations emerged immediately after the creation of quantum mechanics. However, the author of these papers considered the simplest example of free massless Dirac equation. Interest has grown in recent years thanks to new results. With investigation of physically meaningful case, the mass does not equal 0. The interaction potential theta does not equal 0 in our own research. Another approach, the quadratic relations between fermionic and bosonic amplitudes, were found and used in our papers, and here we discuss linear relationship between fermionic and bosonic amplitudes. We have found a relationship between the symmetry properties of the Dirac and Maxwell equations, the complete set of 8 transformations linking these equations, a relationship between the conservation laws for electromagnetic and spinor fields, a relationship between Lagrangian for these fields, and 2 possibilities for quantization. We have also laid the foundation for a classical electrodynamic model of the atom. In recent publications, we add a physical interpretation of these mathematical results. Here I present a review of our results together with new interpretations. The Maxwell-like equation for the electron. In the history of the theoretical physics, the electron appeared within classical electrodynamics as a particle with minimum elementary electric charge, yet there was no place for the electron in the framework of classical electrodynamics of the atom. The difficulties of the Rutherford's purely electrodynamic model of the atom are well known, and the properties of the electron could not be described in the framework of classical electrodynamics. A quest for another theory seemed necessary. Quantum mechanics and quantum electrodynamics were much more successful in the micro-region. Strangely, though, the theory classical electrodynamics could not explain the physical object to which it gave birth. We must therefore answer the question, why can classical electrodynamics not describe its principal fundamental object, the electron? What could be done in classical theory in order to bring it into line with experimental facts of atomic electron physics? The aim of our investigation and our starting point as follows. The electron, as a fundamental object of classical electrodynamics, must be described in the framework of this theory without recourse to quantum mechanics or quantum electrodynamics. The solution should exist within classical electrodynamics. The result of our investigation has opened up this possibility. However, the equations we used were slightly generalized Maxwell equations. The interaction electrodynamics of the micro world, the interatomic electrodynamics of the micro world appears to be to require more general Maxwell-like equations than ordinary Maxwell equations of the micro world. Further, our electron is a wave object, not a particle. The slightly generalized Maxwell equations are considered in a specific medium, the model that models the relativistic atom. It is easily seen that they differ from standard Maxwell electrodynamics by the presence of magnetic sources. In one interpretation are scalar fields, and another interpretation the slightly generalized Maxwell equations in the medium, representing a system of coupled electromagnetic and scalar fields. So he's saying this sort of the electron is a derived phenomena from sort of the background. The generalization of standard Maxwell equations was not undertaken without motivation. There is no doubt that classical Maxwell electrodynamics of the micro world, without generalization, is sufficient to describe electrodynamic phenomena in the macro region. So his basic idea is what we consider the electron is interactions between fields, and you can get there classically, which is kind of, it's interesting how often you don't need to make appeals to, extra dimensions and those kinds of things. But his theory is very mathematically dense, and there's not much that it really offers to understanding the ontological nature of things. So, which is kind of weird because he's the reason he put this book together was try to accomplish that. And his theory, his particular theory, does very little to contribute. Okay, now we'll go to the next one. What caused the electron to weigh? Malcolm McGregor, Santa Cruz, California. In his book on Albert Einstein entitled Subtleties of the Lord, which was published in 1982, Abram Paz has a section called Electromagnetic Mass, the First Century. The last two sentences of this section summarize his conclusions. These sentences: recently unified field theories have taught us that the mass of the electron is certainly not purely electromagnetic in nature. But we still do not know what caused the electron to weigh. In the present article, we discuss various ideas that bear on this problem. Recent discoveries in physics have sharpened our interest, but they have not yet provided answers. Okay, so the concept of mass in physics. Our idea about the concept of mass has gone through several stages of development in the past few centuries, and in particular in the past few decades. During this period, our ability to observe masses, or at least the effect of masses, has dramatically increased, both in the very small scale of the atom and the very large scale of the universe. In the 17th through 19th centuries, our knowledge of masses seemed to be in pretty good shape. The Newtonian laws of motion delineated the inertial properties of massive objects, and the experiments of Ertfos demonstrated that the gravitational mass is the same as the inertial mass. Physicists didn't worry about the way mass is distributed in elementary particles or atoms because there was no way of observing them, and there was no clear proof that they even existed. Astrophysics didn't worry about distribution of mass in an expanding universe because that was not one of their concepts. The discovery of the electron in 1897 ushered in a modern age of observations at the atomic level, and the development of large telescopes in the early 20th century started our exploration of space and time on an extragalactic scale. These new observational skills have led us into the domains where the behavior of masses is not at all what we're expecting, both in the very small and the very large, and these new discoveries has, as of now, raised more questions than they have answered, even in the case of the ubiquitous electron. The concept of electric charge is as mysterious in its fundamental reality as is the concept of mass. We have known since Benjamin Franklin's time that the charge comes in two matching forms, which we label positive and negative. A stationary charge gives rise to an electrostatic field that acts on charges and perhaps also itself. A moving charge gives rise to an electrostatic field and a magnetic field. A moving observer looking at, to us, a stationary charge sees both fields, whereas we see just one. The nature of these electromagnetic fields, which can exist in a medium or in the vacuum state, has never been clearly revealed, nor has the nature of the electric charge that generates them. We might think that there should also be a magnetic charge, but persistent searches have failed to find it. Chemical experiments in the 19th century made it clear that electric charge exists in a quantized form rather than as a continuous fluid of some kind. The identification of the electron by Thomson and others showed that it is a carrier of the unit charge, and that it might, in fact, simply be the charge. Electron-electron scattering experiments carried out in the mid-20th century indicates that the charge on the electron is concentrated in a very small area. In fact, it has no measurable size at all, down to length, the scales of 10 to the minus 16th centimeter. If this point charge is at all there, it is to the electron, then the large values observed for its spin, angular momentum, and magnetic moment are results for which we have no conventional explanation, since these values, if calculated from the standard formulas of mechanics, electrodynamic, required a length scale of roughly 10 to the 11th centimeters. The puzzle about the actual size of the electron is compounded when we move to the other basic massive particle, the proton. The proton carries the charge positive, but where the absolute value of E is precisely the same as that of the electron. The proton also has the same spin as the electron, and it has a magnetic moment. But unlike the electron, the proton has a finite electromagnetic size of about a Fermi, that is 10 to the minus 13 centimeters. The crucial point here is that the measured size of the proton is in fact roughly what we would expect theoretically from the values of its spin and magnetic moment. Why should the proton, with its classically scaled spectroscopy, be so different from the supposedly point-like electron with its inexplicable spectroscopy? This is really a question about theory more than experiment. The experimentally observed elementary particles have mass values that were not anticipated and are not understood. But we might expect that the theory, which gives us some guidance about spectroscopy of the proton, should do the same for the electron, and perhaps, as we suggest below, it might do just that, but with a required extension of our concept of mass. When we move from protons to quarks, the substates that make up protons and neutrons, the mass mystery becomes even deeper. When quarks were first postulated by Gell-Mann and Niemann, it was assumed that with enough energy we could knock a proton apart into its basic components. When this failed to happen, it was attributed to the fact that proton quarks are very massive and have large binding energies. When collision energies got very high and quarks still didn't appear, it became apparent that this was not the answer. A different type of binding mechanism based on gluons was proposed, and proton quarks themselves were not assumed to have very small masses. were now assumed to have very small masses, with almost all of the proton mass arising from the quark-gluon plasma. Further mass mysteries awaited us in outer space. Modern telescopes enable us to examine large spiral galaxies in detail, and it became apparent that these galaxies do not contain enough visible matter to hold them together gravitationally at the observed rotational rates. They must have some kind of dark matter that is clumped in the outer regions of the galaxies. Also, the existence of black holes is required in order to explain tremendous energy output of quasars. Now I don't believe the black holes and the dark matter are correct. It's too bad this book does not contain the electric universe theories. I think this author would have used them if he was aware of them. He would have had a contribution from Walt Thornehill or somebody. But at any rate, there's a problem. Okay, and Birkeland currents, intergalactic electromagnetic currents could explain it without any appeals to black holes and dark matter. But at any rate, still another result, the Casimir effect demonstrated that if we were hold two plates close together in a vacuum, there is an attraction between them that is generated by the ceaseless production and annihilation of charged pairs in the vacuum, the so-called zero-point energy. Thus empty space is not really empty. I have never seen yet, nobody's ever answered my question, is where in the Casimir equations is there subtraction for the gravitational attraction between the plates? I don't understand how you distinguish between that and gravity. There must be some. I'm assuming it's being done, but I don't see it. As we enter in the 21st century, further refinements of our concepts of mass are being forced upon us. Neutrinos, antineutrinos are electrically neutral leptons, which are emitted, for example, neutron, muon, and tau decay. Postulated and then identified in 20th century, neutrinos carry energy, spin, and lepton number. Their interactions are so small that they can penetrate through 100 light years worth of lead bricks before they interact with the lead. It was originally believed that neutrinos are massless and travel at the speed of light. However, measurements of electron neutrinos fluxes from the sun indicate that only 1/3 of the expected events are occurring. Recent experiments have confirmed that the electron neutrinos are being transformed into muons and tau muons, and tau neutrinos as they travel through space, which requires that they have finite masses. Since the universe is flooded with neutrinos, even a small neutrino mass causes them to make a substantial but not decisive contribution to the overall mass of the universe. Perhaps the strangest modification in our concept of mass comes from modern cosmology. In the Big Bang Theory, the universe expanded from a point like, which that's another thing, electron universe, we can get rid of the Big Bang. The observations indicate it's still expanding. Space is filled with low energy electromagnetic radiation from the original expansion. In order to explain the gravitational attraction, it has created galaxies and clusters of galaxies. We had to assume the existence of large amounts of dark matter in space. And once again, is an assumption that doesn't need to be made. But in order to simultaneously account for the large expansion rate of the universe, we may also have to assume the existence of vast amounts of observable negative pressure dark energy. So we could just skip over that because it's actually nonsense. All right, one familiar object which also has puzzling mass properties is the photon. The photon has a spin 1. And a circular polarized photon beam can rotate a quarter wave plate, but the photon, unlike the neutrino, has no measurable rest mass, even though it carries energy and momentum. Since an energetic spin one photon can be converted into electron positive and pair of spin 1/2 particles. The spin of the photon must, in some sense, be related to the spin of the electron. Thus, the models we make for these objects must be interrelated. A particle spin is, in principle, a spin angular momentum, which involves an extended mass rotating around a center. Hence, the mass problem emerges in a crucial way in the dual concepts of massless photon and point-like electrons. In the present paper, we bring to bear all of the information we have about the spectroscopy of electron to see what it can tell us about the structure of electron. Many years ago, Albert Einstein, who spent years worrying about the structure of the photon and the structure of gravitational space, made the following observation. You know it would be sufficient to really understand the electron. Okay, that was the statement. Let me see. All right. So this is kind of interesting because now you have the model that's. I kind of like this one because what you're talking about is an electron that is more like a photon. An electron and photon, I mean, things start to take on this property of information. For instance, how if you had a video game simulation, let's say a soccer game, and the soccer player on the video game simulation kicks the soccer ball, there's actually no mass in that video game soccer ball player's a foot, but the ball takes a trajectory that's described mathematically, and that to me I think is probably going to be how these things eventually converge onto. There's got to be a simulation to explain, especially the photon, that this photon being explained as a simulation, that the information goes forward in space the same way it's been programmed to do. It's requiring. Max Planck had a famous quote about this, that what we're going to find underlying all reality is this information matrix that's controlled by a pre-existing intelligence. This is Max Planck. Okay, and I think that's where we're going to end up. Zero rest mass photons, electric waves, particle holes, excitations. So this model is very similar to the Dirac sea. It almost it's as if. Here's one. Listen to these chapters. These are pretty good. A dynamical basis for the de Broglie superluminal phase velocity, mechanical masses and constituent quarks, the mass of the neutrino. This is kind of the concluding. Let me just read this. The massive analysis of the present paper, we demonstrated that the spin angular momentum of the electron could be reproduced by a Compton-sized relativistically spinning sphere of non-interacting mechanical matter. We also reproduced the spin angular momentum of the massless photon by rotation of pH as particle hole excitations of the vacuum state. These results suggest that a particle such as a neutrino, which carries a spin 1/2, should logically have a mass that is responsible for its spin. If we start with the RSS electron model shown and then remove its charge, we are left with a spinning sphere of matter that has a spin 1/2 that does not interact appreciably with other objects, and that carries a left-time quantum number. These are the salient properties of the neutrino. Hence, the studies of the electron imply that spin 1/2 neutrons have masses. At the same time, these ideas were first set forth. The prevailing view was neutrinos are charily invariant particles which have zero rest mass and travel at the velocity of light. Thus, the recent confirmation of the finite mass of the neutrino serves to reinforce the present notion that where there is spin angular momentum, there is also mass. RSS, I forget what that stands for in his model. I forget what that is. Maybe rotational spin state. Anyway, all right. Let's look at. We'll go on here now. This next chapter. Electron in 3+3 dimensional space-time. Paolo Laciani and Robert Mignani, Italy, right, Roma. We review the basic features of a model of the electron in a 6-dimensional space-time. 2 extra time dimensions. The electron is assumed to be a massless particle in this space, and it acquires mass when considered in the actual 4D space-time. Its spin and magnetic moment are obtained by an effect of polarization, which gives rise to the 3-dimensional temporal space, to a helicoidal motion along the usual time axis with radius of the order of the Compton wavelength of the electron. In this model, chirality is nothing but the direction of rotation of the electron in the time space. It is also shown that a connection can be established between 6D space-time and a recently developed Kaluza-Klein-like formalism with energy as a 5th dimension. Introduction. Time and electron. How many times? What is time? Many definitions exist, all very different one from the other, from psychological to physical. For example, Ravelli has analyzed the distinct roles that the notion of time plays in different scientific theories and found 10 versions of the concept of time, from natural time to no time, all used in natural sciences. From physical point of view and in the framework of special relativity, time is the 4th dimension of the Minkowski space-time, namely the component of the position 4 vector. This representation is so well established experimentally that a necessary requirement to be satisfied by any physically acceptable theory is its Lorentz covariance in space-time with 4 dimensions, 3 space-like and 1 time-like. It is well known there is no experimental evidence that time has more than 1 dimension in our universe. This is obvious since any matter with a different time direction would remain observable only for a very short time before disappearing almost immediately. For example, had particles have been created during the Big Bang with more than one initial common time direction, they would have been immediately separated, and now only those with the same time would constitute our universe. Look at the hypothesis by Stuckelberg. And Feynman. Okay, the antimatter corresponds to particles traveling backwards in time, can explain why the universe does not seem to contain the same amount of matter and antimatter. However, if space-time is a physical concept and not only a mathematical representation as suggested by Einstein's special theory of relativity, the question arises, why do 3 space coordinates and only 1 time coordinate exist? The idea of a multidimensional time was considered in the second half of the past century mainly as a possible tool to explain quantum features in a semi-classical framework. In particular, the problem of possible symmetry in the number of dimensions in space-time was noticed in the early 70s in the framework of generalization of special relativity to faster and light speeds. Indeed, the superluminal Lorentz transformations in the 4 dimensions introduced by Racimi and one of the present authors changed the sign of the space-time interval, thus mapping space-like dimensions into time-like ones and vice versa. This leads to, in a natural way, to the hypothesis of an equal number of time and space dimensions, following Demers, who assumed a 3 plus 3 dimensional space-time and applied it to some aspects of trichromatism. Magani and Racimi introduced a time vector in order to explain the appearance of the imaginary quantities entering into the 4D generalization of Lorentz transformations. A space-time point in the space is therefore represented by a 6 vector. In agreement with Demers, it was assumed that only modules the only modulus is physically observable for bradyons, that is slower than light particles, whereas only the modulus of this new vector is a meaningful quantity for tachyons, faster than light particles. Okay, it's going to get real complex real quick. Okay, so basically, it's a pretty interesting. I always wondered about that. Why don't we treat time three-dimensionally, past, present, and future? Philosophically speaking, this idea that I don't like this. I don't like this idea that God is outside of time. It seems to me that God encompasses all time, past, present, and future simultaneously. That's why people have these near-death experiences and so forth. They have this your sense of time becomes eternal, sort of. It's like an eternal now kind of thing. And that would explain an awful lot. I mean, if that's the I don't know if you call it a substrate, but I don't know what you'd call. Okay, if our universe is inside of something else, I'll call it a substratum just because I don't know what else to call it. But so that's what we're inside of. So the thing that gives us this, this thing that gives us a finite finitude is the fact that we have just experienced the present time dimension. And, it makes a lot of sense. And so these guys are just applying it to the electron as it exhibits any kind of quantum behavior, and as a way of getting around the problem of, is it point-like, or does it have these extension in space? I'd have to reread that. It's been a while since I read that. I have to reread it to really wrap my mind around it. Let me see here. Let's go to the conclusion. The main advantage of the model of the electron in a 3 plus 3 space-time we have described can be summarized as follows. The mass of the electron, which is assumed to be a massless particle in 6D space, is obtained from 6D Klein-Gordon equation as an integration constant. The usual expression, and therefore the experimental values of the spin and the magnetic moment, are derived by assuming an attractive force due to vacuum polarization in the usual space-time along the radial time direction in the extra-dimensional plane. The direction of both of them is always orthogonal to this plane and therefore parallel to the standard time direction. The origin of the electron spin is due to the helicoidal motion of the electron in time 3 space. Mass quantization follows from an assumed discontinuity in the attractive potential. This discontinuity can be generated, for example, by the presence of a virtual pair of charged particles somewhere between the center of rotation of the electron and its actual position in time subspace. In this model, chirality is nothing but the inverse of electron rotation in time-space. We have also shown that a connection can be established between 6D spacetime and the recently developed Kaluza-Klein-like formalism with energy as a fifth dimension. In conclusion, the modern electron with two extra dimensions seems to provide a good representation of its known properties. However, many questions still remain unanswered, in particular concerning the applicability of the model to other charged leptons. It is also an open problem how neutrinos fit in this scheme. A possible test of the reliability of the model involves chirality, which work presently in progress to establish the feasibility of a specific experiment. In the meantime, the model of electron presented here would appear physically sensible and suggests that 3D space is perhaps something more than a mathematical hypothesis, which is pretty interesting. Okay, so he's, basically just saying, if you treat it like the electron has qualities of the electron are derived from the fact that it doesn't all exist in our present time dimension. And that makes a lot of sense to me too. But it's still going to. I think everything's still going to converge on this information matrix. I think that's eventually when we get to the bottom of this. If we ever get to the bottom of it, you have to make an appeal to the information matrix. Okay, let's go to the next paper. Can studying the inertial and gravitational properties of the electron provide us with an insight into its nature? Veselin Petkov, Concordia University, Canada, Quebec, Canada. It's shown that both the classical spherical electron and a point-light electron considered in the framework of quantum electrodynamics predict the correct form of the expressions for the inertial and gravitational forces acting on a non-inertial electron. Surprisingly, the two models turn out to be indistinguishable if formulated in terms of a radically new idea of the electron structure, which he's calling four-atomism, which explains why the correct forms of the expressions for the inertial and gravitational forces can be derived from the two models. The idea also appears to shed some light on a number of quantum mechanical puzzles. Introduction: studies of the nature of the electron deal as a rule with its quantum mechanical features. This paper takes a different approach. In section 2, the inertia and the gravitation of the classical electron are discussed. The classical model regarding the electron as a small charged sphere leads to correct expressions for the inertial force acting on an accelerating electron and for the gravitational force acting on an electron at rest in a gravitational field. As these forces originate from the interaction of different elements of the charged sphere representing the classical electron, it is concluded that their derivation from the classical model is an indication that the real electron is unlikely to be a point-like particle of a size smaller than 10 to the minus 18 meters, as experiments probing its scattering properties appear to suggest. In section 3, the inertial and gravitational properties of the electron in terms of quantum electrodynamics are studied. It is shown that a point-like model of the electron in QED yields expressions for the inertial and gravitational forces in which the forces are proportional to the acceleration and mass of the electron. Section 4 analyzes arguments that indicate the electron cannot be a point-like object and considers a model of four-atomism which appears to resolve several puzzles. Why is an electron not localized when not measured? The stability problem of the classical electron. The meaning of the scattering experiments according to which the electron appears to be a particle localized in an area of dimensions smaller than 10 to the minus 18 meters, which contradicts the wave-like nature of the electron. And why do both the classical electron and a point-like electron in QED lead to correct forms of expression in the inertial gravitational forces acting on a non-inertial electron accelerating and supported in a gravitational field, respectively. It is also shown in the last section that a four-atomistic model of the electron may shed light on a number of difficult quantum mechanical problems. Inertial gravitational properties of the classical electron. In the classical model of the electron, its charge is uniformly distributed on a spherical shell. This model offers a mechanism responsible for the electron's inertia and mass, the repulsion charge, elements of the electron in uniform motion, cancels out exactly, and there is no net force acting on the electron. If, however, the electron is accelerated with respect to inertial reference frame, its electronic field distorts, which causes the repulsion of the elements to become unbalanced. As a result, the non-inertial accelerated electron experiences self-force that resists this acceleration. It is precisely this resistance that we call inertia, and why repulsion in the different parts of the accelerating electron become unbalanced is explained elsewhere. The calculation of self-force is easier in non-inertial accelerator reference frame in which the electron is at rest. At first, it appears that the field of the electron is not distorted since it is at rest, which would mean that no force is acting on the electron. If this were the case, there would be a problem. An inertial observer and a non-inertial observer would disagree whether or not the electron is subjected to a force. As the existence of a force is an absolute fact, all observers should recognize it. This problem disappears when a corollary of general relativity that the average velocity of light in a non-inertial reference frame is anisotropic is taken into account in the calculation of the electron field. The average anisotropic velocity of electromagnetic disturbance, where, let me see, the property of acceleration and the radius vector representing the path of the light signal between the 2 points separated by a distance r. The anisotropic velocity of light causes the distortion of the electric field of the electron. As a result, the balance of the neutral repulsion of all of the parts of the charged elements of the spherical shell representing the classical electron is disturbed, and the resulting net self-force acting on the electron turns out to be precisely equal to the inertial force. Which is kind of, it's a really interesting idea. This way, it's kind of like synchronizing, the old World War I fighter airplanes, synchronizing the machine gun bullets with the space in between the propeller blade. Which is actually really interesting and probably is the right. I mean, that makes a lot of sense. It makes an awful lot of sense. Is it kind of... I mean, there's something in most of these theories I really appreciate. On the nature of the electron, we started with the intention to see whether the study of the inertial and gravitational properties of the electron can help us gain some understanding of its nature. Instead, it appears we have obtained contradictory results. The classical model of the electron leads to correct expressions for the inertial and gravitational forces acting on accelerating electron and on electronic rest in a gravitational field, respectively. Those expressions cannot be attained if the electron is point-like. In quantum electrodynamics, however, it is a point-like electron whose semi-classical treatment yields the correct form of the expression for the inertial and gravitational forces acting on it. It is precisely this apparent paradoxical result that may provide some insight into the nature of the electron. At first, it might seem that a point-like model of the electron may be closer to what the real electron is due to the experimental evidence putting an upper limit 10 to the minus 18 meters on the electron size mentioned in the introduction, and the stability problem of the classical electron, according to which it cannot be stable since its charge will tend to explode. However, there exist strong arguments against a point-like electron. As one of the most difficult problems of the classical electron, it is stability. One may conclude that the basic assumption in the classical model of the electron is that there is interaction between the elements of its charge may be wrong. The very existence of a radiation reaction force, however, is evidence that there is indeed interaction, that is repulsion between the different parts of the electron charge. The radiation reaction is due to the force of the charge on itself, or more elaborately, the net force exerted by the fields generated by different parts of the charge distribution acting on one another. In the case of a single radiating electron, the presence of a radiation reaction force implies interaction of different parts of the electron. Therefore, not only does the classical model of the electron yield the correct expression for the inertial and gravitational forces acting on the non-inertial classical electron, accelerating and at rest in the gravitational field respectively, but also reflects an important and puzzling feature of the real electron, the self-interaction of its charge. The strongest argument against a point-like electron, however, comes from quantum mechanics, despite all studies devoted to the nature of the electron. No one knows what an electron looks like because being detected at some even deny the very correctness of such a question. One thing, however, is completely clear. The experimental upper limit on the size of the electron, less than 10 to the minus 18 meters, cannot be interpreted to mean that the electron is point-like particle localized in such a region without contradicting both quantum mechanics and the existing experimental evidence. Let us consider an example which clearly demonstrates why, according to quantum mechanics, the real electron cannot be localized point-like particle. The hydrogen atom does not possess a dipole moment when its electron is in an S state. It is difficult to explain why so little attention has been paid to the fact that this is only possible if the electron is not localized somewhere above the nucleus, but somehow occupies the spherical region for a short shell around the nucleus where its wave function is different from zero. It should be stressed that this example leaves us with no choice about the interpretation of non-zero probability of finding the electron in the spherical shell. The electron must actually occupy the whole shell. Otherwise, if it were as small as the scattering experiment seemed to suggest, the hydrogen atom with its electron in the S state would certainly have a dipole moment. Therefore, the experimentally determined size of the electron tells us very little about what the electron itself is and needs further studies in order to understand the meaning of its size. The example with the S electron and the hydrogen atom is important to respects. First, it shows that the argument that there should be a stability problem in the case of classical electron applies equally to an electron in S state when we take it into account that the S electron must actually exist in the whole spherical shell where its wave function is different from zero, strictly speaking. It applies to all electrons and atoms. In that state, the electron is like the classical electron, a charged spherical shell, which should tend to blow up due to the repulsion of its different parts. But it does not, which further deepens the mystery of the electron. It seems there is no stability problem for an S electron, and no one knows why. This implies that there should be no such problem for the classical electron either. Second, the hydrogen atom example clearly demonstrates that perhaps the greatest mystery we have to solve in order to understand the nature of the electron is how can an electron occupy the whole region where its wave function is different from zero when it is not measured, whereas the electron is always measured as a localized entity, a point-like particle. As this mystery has persisted for decades, any idea sufficiently radical to have some chance of surviving both theoretical and experimental scrutiny should be studied thoroughly. I will briefly discuss such a radical idea here since it offers a possible simultaneous resolution to the mysteries mentioned above. How can an electron be an extended object before measurement, but always be measured as a point-like particle? And why is there no stability problem? Why does a charged spherical shell not blow up? The idea was proposed by Anastasov in 1980s, but unfortunately remained unnoticed and untested. Its essence is bringing the idea of atomism to its logical completion, discreteness, not only in space but in time as well, for atomism in the four atomistic model, An electron is represented not by its world line as deterministically described in special relativity, but by a set of four-dimensional point-like objects, for short 4D points, modeled by the energy momentum tensor of dust, in this case a sum of delta functions. We can regard these objects as points of disintegrated world line of the electron. Those 4D points are scattered all over the space-time region in which the wave function of the electron is different from zero. Okay, well, I guess I can read the rest of his 4D atomistic thing, but I don't think it's going to clear things up too much. I'll just read the first paragraph here. Okay, the atomistic approach sheds light on the physical meaning of the Compton frequency of the electron. For 1 second, the electron is represented by a 10 to the 20th 4D points. By 10 to the 20th 4D points, which means that the constituents of the electron appear and disappear with Compton frequency. It follows from here that during a given period of time, when not measured, the electron is everywhere in the region where there exists a non-zero probability of finding it. However, the electron is always measured as a point-like particle, since when the first 4D point appears in the detector, it is trapped there. There is a jump in the boundary conditions of the electron wave function, and all consequent 4D points of the electron start to appear and disappear in the detector as well. That's kind of... Okay, the conclusion. The correct form of the expressions for the inertial and gravitational forces acting on a non-inertial electron are obtained from two different models of the electron, the classical spherical electron and the point-like electron considered in the framework of QED. It turns out that both models yield correct predictions, since there is no fundamental difference between them if they are expressed in terms of radically new ideas of the electron structure for atomism. The idea also shed lights on a number of quantum mechanical properties. So, basically what he's trying to do is construct some kind of model that allows it to, allows the electron to have its existence, most of its existence in other dimensions. It's also kind of like a Dirac sea. The idea that what we experience of the electron is just the part of it that interfaces with our 4D, our 4 space-time dimension, and that in a sense the electron, there could be just one electron, and at that point. Okay, next one. The electron is a periodic waveform, spin 1/2 symmetry. Horace Drew, South Wales, Australia. Authors write many things, and the common people cling to them through arguments made without experiment. That was Roger Bacon. That's the quote. Okay, on experimental science. Most current theories in physics or astronomy are not unique. I think this is... I don't know if I should end this at like a certain part, or should I just keep going and have a real long video? I think what I'll do is, I'm about an hour now. I guess I'll keep these to about an hour. We'll get into this next chapter. This in the next video. I guess that's how I'll do it. Just because I'm not sure what the cutoff point is for if I can make real long videos on library or not. It seems like I'm making longer ones, but I'm not absolutely sure. So let's end that part here. We'll call this part 3. We'll start part 4 some other time. I think what I'll do, maybe I'll switch books and go to part 4 later. But thanks for watching. If you did watch, nobody watched part 2, so I don't know. I doubt part 3. And I will be I will continue to make commentary about following Christ in the way we interpret geopolitics, and so forth. So, I'm not like switching. I'm just, adding variety to my channel. I just don't want to just do one thing. I mean, I just don't do one thing in reality. I, don't want to just do one thing online either. And I understand, the people who really concentrate on, focus on one topic. They have popular. That's the way to get popular. But I'm not about popularity. I just want to, this is share different things that I'm interested in. This is one of my always been interested in fundamental physics, theoretical physics and so forth, and all for the purpose of understanding sort of the nature of reality, and to me, understanding that is ties into a biblical mandate to see nature and interpret it as a way of worshiping God. That understanding nature and understanding how things works is actually a way of appreciating God's creation. That's a form of worship. I mean, it should be. I'm not. There's an awful lot of people that use this in the opposite way. They use it to try to establish a foundation to deny the existence of God, and I think that's just not the right way to going about it. You're never going to get a coherent ontology. You're never going to get a coherent interpretation of the nature of reality. You got to start by allowing a pre-existing intelligence, omniscience, omnipotence, omnipresence, and eternal. That's, to me, that's the right way to establish your foundation and go from there. So, but not everybody sees it that way, and that's right. I enjoy discussing with people the different ways of approaching interpreting reality and so forth. I mean, I don't. Here's the thing: there's three ways to interact with people. One is not to share what you really think and just get along with everybody. The other way is to share what you really think, but give people room to differ. And the third way is to share what you think and insist that other people agree with you. And unfortunately, the third way is the common way. The first way is probably the second most common, and the in-between way of sharing what you really think and giving people lots of room to have differ from you. That's to me that's the correct way, but that's the least common way for people to behave and interact with one another for whatever reason. Anyway, I'm Sean Maurer. This is Love and Division. I should start. If library comes up with playlists, I'll have a book review playlist, and maybe I'll have one, for science and physics and so forth, and we'll put it in there. Maybe philosophy and religion. All right, see you guys. Thanks. Bye.